Hi, so today we're going to be talking about bridges some more. This is Junior. He is my cat, and he was quite unhappy that only the dog was featured in yesterday's videos and that the cats were not featured at all. Junior's real name is Sean Jr. I got him from the Humane Society, and his name was already Sean, but my son's name is also Sean, and I thought it was a little weird to name my cat after my son, so that's why his name is Sean Jr. So today, with the help of my cats, we're going to learn a little bit of the science behind bridges, and then you will have a project to do to work on today when you're done with the video. So here are my cats crossing a bridge in my house. So I would say that this is just a simple style of bridge, but it would still count as a bridge. So today you're going to look at bridges, 7 different types of bridges to be exact. And this would be like a plank bridge, for example. I mean, even a tree just across a river is a type of bridge. But as the loads get heavier, both these cats only weigh about 8 pounds. My Maine Coon cat, who weighs 22 pounds, he wouldn't get on the bridge. Maybe he knows his load is too much. So as the loads get heavier, as the distance gets longer, then the bridges have to use different structures in order to be able to function correctly. Here is Junior with Chubbs. Chubbs is a cat I adopted from the streets, and his name is Chubbs, which seems silly, but when I got him, he was much rounder looking face, and so he got the name Chubbs. Now he's the smallest of all my pets. So I do want to remind you before we go on what a force is. So a force is a push or pull on any kind of object. So we have all sorts of different types of forces. We have forces due to gravity, we have compressional forces, we have torsional forces, we have tensile force, we have forces that act in different ways. And a couple of these are going to be very important for bridges. If you remember, our formula for force is force equal mass times acceleration. So here we have compressional force. It's going to be one of the forces that are very important when we talk about bridges and how they work. So here we have a material being squished between two forces. So that's an example of compressional forces. On the bridge, obviously the truck is putting compressional forces on the road, but also even these big columns have compressional forces because these are a lot of times made of something like concrete. So that is a lot of mass that is then putting a force downward on them. We also use things like in our cars, our disc brakes they work by using compressional forces also. In addition, we have tension forces. So tension forces are kind of the opposite. Instead of being squished, it's when something is being pulled. So here we have a tension force between two people playing tug of war, and here we have a tension force of the wreck and ball, and notice the tension force in an upward direction. So next I'm going to show you a video of Junior and Chubbs. No, I think it's Chubbs trying to explain what tension forces are, and then Junior will help me explain what compressional forces are. Thank you.
So I'm here with Junior, and we're just going to do a little experiment with compression forces. So I just have regular eggs. They're not hard boiled yet. I put 4 of them out. So remember, a compression force is just something that like squeezes or compresses things on both sides. So I got the table on one side of the egg. That's going to be putting an upward force on the egg. And then I'm going to stack books on top of the eggs. So I'll just put a book on there. You can see the eggs underneath. So something that's unusual about compression forces is what I stack the books on cannot change the amount of force at all. However, it does change the way the force is distributed. So as we study bridges, here goes another book. So far, so good. Zeus is also watching this experiment. So while I can't change the amount of force that the books are exerting downward, their force is equal to the mass times the acceleration of gravity, and it's being pulled straight down. The eggs have a shape that can distribute that force, and of course they also are made of a certain type of material. So both are going to be important with bridges, both the shape of the bridge and the material it's made of. So here goes the next book. Lots of heavy science books here going on top. So far, my eggs still stand. I think we'll hear them when they decide to crack. Here goes my next book. Okay, before they crack, here I want to do a little experiment. We'll come over here to Junior and see if he will help me out. Come here, Junior. You're going to be part of science. So this is Junior. And he is going to sit on the books. That adds about another 7 pounds. So I'm putting Junior on top the books, and they're still not cracking. But he doesn't much like it up there, so he's getting down. So let's keep adding books. So I just added another book. They're still not cracking. I may run out of books here. I may have to go get some more. Yep, the eggs are still holding here. So you see I got all sorts of books. I love to do flowers, so I have dried flower books. I love to paint and draw, although I don't make enough time for it. So let's put Junior up there again and see if we can get the eggs to crack. Yeah, they're still not cracking. He weighs about 8 pounds. I don't think I can get Zeus to sit up there, so we won't be able to do that. Well, now he's going to just settle in. So let me move him off so I can keep adding books. I've got a heavy one here. I'll go ahead and, oh, this one's very heavy. What is this? This is the Encyclopedia of Plants. So let's put that up there. Oh my goodness. So my eggs did not crack, and I'm sort of out of books here to Woo! Okay. All that noise was my animals running away, and finally the eggs cracked. So this is Chubbs. He is a stray I adopted. Notice him demonstrating tensional forces. He has Skunky on a string, and I'm pulling the string this way, pulling it. Oh, it just bounced off, so let's try again. A tensional force is just when there are forces. Right now he's just doing regular old forces. He's got to grab it. He's got to grab it, grab it. Once he grabs it, and then when I pull on it, that's a tensional force because he's got one end and I have the other end. So bridges have to also use tensional forces. Even the bridges that aren't suspension bridges use a lot of tensional forces. So there's Chubbs. So wave goodbye to Chubbs.
So as you saw, structure can be very important when it comes to helping compressional forces being distributed, and the triangle is one of the strongest shapes. And so I want you to do a little bit of research about why it is that triangles do help to distribute that load and to strengthen the bridge in so many ways. But if you look at pictures of those bridges now that you looked at earlier, and you start to hunt for the triangles, you are going to get to see them everywhere in the structure of the bridges, because triangles are an incredibly strong shape in helping to distribute the forces that are acting on the bridge. So here's a picture from the Deception Pass Bridge that I showed you yesterday. And now that you look at it, can you identify the triangles at work within this bridge? Like, I know it's a hard angle, but just looking right here, you can pick out some of the triangles. And here is the bridge, just the Spencer Island Bridge. Not a very far bridge, but too far to just have a plank going across. So again, if you see these triangular structures and start to understand why they are used in bridges, and so your assignment is going to be making a PowerPoint and explaining the structures of the different types of bridges, and that assignment will be found on Canvas.